Welcome to Ordinals, the easy introduction. Well, we're not really going to be going in a rigorous fashion over ordinals, just kind of explaining the general idea and kind of like building up to talk about, the fast-growing hierarchy just for fun, just to have some fun. So let's get started on this topic. Here I have a set of 3 elements with a binary relation on the set. This thing is called a relational structure. Now this binary relation is going to arrange these elements in a certain way. So here I have the first thing is less than the second thing, and the second thing is less than the third thing, and the first thing is less than the third thing. That's why I call them first thing, second thing, third thing. Now here I have a possibly different relational structure because it has some possibly different elements here. But its binary relation is going to arrange its elements in exactly the same way. So while these two relational structures might not be identical to one another because they might have different underlying elements, they are the same as each other if you ignore what the elements are and just focus on how they're arranged by their binary relations. Because they're both arranged like this, 3 things in a row. Now these are special kinds of relational structures because their binary relations are called strict well orderings, which I'll explain what that is. But ordinal numbers are a system of numbers that basically tell you what type of strict well ordering you're dealing with. So in this case, the ordinal number 3 is going to tell us what kinds of strict well orderings these are. It basically tells us how long the arrangement of elements is in the strict well orderings. An ordinal number represents the order type of a strict well ordering. Well, here I have an example of something called a strict linear ordering, which takes us almost all the way to a strict well ordering. It's got 3 axioms here. There's just one more axiom you need to have a strict well ordering. So a good example of a strict linear ordering is the real numbers with the standard less than relationship. So here I've got x, y, and z just for instance. So the first axiom says that it is never the case that x is less than x. That's called irreflexivity. The second axiom says that if x is less than y and y is less than z, then x is less than z. That's called transitivity. And the third axiom says that at least one of these 3 has to be the case. Either x is less than y, or y is less than x, or x equals y, called totality. Now, strictly speaking, this allows for multiples of these to be true, but when you combine it with these other 2 axioms, it forces exactly one of these 3 things to be true. And this is the axiom. If you just have these 2 axioms, you have sort of like these branching, it sort of has like the logic of an ordering, except some elements might not be comparable. This third axiom forces everything to be comparable. That's kind of squashing everything into a linear arrangement. Now we will combine those 3 axioms with one more axiom to get a strict well ordering. And that's going to be the axiom that says that any subset must have a least element. Well, there's just one catch. I just said any subset has a least element. That is, any sub-collection has a least element. Well, the empty set is always going to be a subset, but the empty set has no elements. So having no elements, it certainly doesn't have a least element. So, okay, we'll just exclude that one then. Any non-empty subset has to have a least element within itself, okay? So going back to our strict linear ordering, the real numbers with standard ordering, It's not well-founded, which is this property I just described. Because, for instance, if I have the open interval 0 to 1, this is a non-empty subset. It certainly has at least one element in it, in fact, uncountably infinitely many elements within it. But it doesn't contain a least element of itself. You might say, well, wait, maybe 0 is the least element. But does it contain 0? No, it doesn't, right? And then if you try to pick something like 0.1, well, that's certainly not the least element, because then you have 0.01, which is still in the set, but less than that. So it doesn't have a least element here. So it's not well-founded. An example of a well-founded, something that is well-founded would be the natural numbers with the standard ordering on them, which I've kind of drawn here with these notches. Now, any non-empty subset of natural numbers certainly is going to have a least element, right? If I don't know, take this subset here, well, this notch here will be the least element of it, right? And you can always add 1 to an ordinal, you know what I mean? Like, if I have omega, I can add an element that's greater than all the elements in omega, and that's omega plus 1. And then I can add an element that's greater than all the elements in omega plus 1, and that's omega plus 1 plus 1, or omega plus 2. I'm just extending an ordinal by one more step when I add 1. This is alpha plus 1, alpha being any ordinal. You can always add 1, just like in the natural numbers. It's great. Now here's something else you can do with ordinals. For any set of ordinals, there's always going to be a least ordinal that's greater than any ordinal in that set. In particular, you can do this with sequences. So here I have the sequence of natural numbers. What's the least ordinal greater than all the natural numbers? Well, it's omega. And then I can always add 1 to anything, so omega plus 1, omega plus 1 plus 1. I can do that forever. Wait a minute, what's the first ordinal that's greater than any of these ordinals? Greater than any ordinal of the form omega plus n, where n is a natural number? Well, it's going to actually be something we'll call omega plus omega. Now, I haven't defined what this addition is all about, but you know, this is not a rigorous video. I might do that another time if I'm ever able to. Another way to write omega plus omega is omega times 2. Omega times 2 plus 1. Omega times 2 plus 2. What's the first thing greater than all of those? Omega times 3. So here's what omega plus omega looks like. It's kind of like I just have omega here, and then I add a copy of omega after omega. So any element in here is going to be greater than all of these elements, as well as being arranged, you know, how they are. So like this element right here is obviously greater than this one, which is greater than this one, and they're all greater than all of these, right? So omega plus omega plus omega is just going to be, you know, 3 copies of the natural numbers, one after the other. Now we'll stop by going up to omega squared. So we had omega, omega times 2, omega times 3, and in a similar way you can get omega times 4. You can build up all of those, and then there's the first ordinal beyond all of these ordinals is going to be omega times omega, which is omega squared. So here, see these orange notches, 1, 2, you know, 0, 1, 2, 3, 4, 5, 6, on and on and on forever. So these orange notches are like omega right here, right? These orange notches are like omega. And then I'm going to take each of these orange notches and replace it with a copy of omega. So here I'm taking this orange notch and replacing it with a copy of omega. I take this orange notch and replace it with a copy of omega. And I'm going to do that. So I'm taking omega number of notches and replacing each of them with omega number of notches. And that's going to give me omega squared. So, you know, this is pretty long, but it's still countably infinite. And, you know, just like with how the natural numbers, like every natural number is small, right, in a sense. In the same way, every ordinal is small, in a sense. Like, just how, like, for any natural number, there's infinitely many natural numbers greater than it, but only finitely many natural numbers smaller than it. Well, for any ordinal you can think of, there's going to be, you know, some number of ordinals smaller than that ordinal, you know, perhaps infinitely many of some cardinality, but the number of ordinals beyond an ordinal is going to be beyond any cardinality. And I always really wanted to make a video about that, but you know, health and all. But yeah, let me know if you have any questions, if you found this interesting, yeah, or anything, any comments. I would love to hear it. Thank you, and take care.